Next, we're going to explore a different approach for finding simpler decision trees. We're going to grow them all the way, and then we're going to start pruning. And the way we're going to prune it is kind of like early stopping criteria 2. We're going to prune things that don't improve our classification error enough. So we have two ways to try to find simpler trees. One way was to stop recursing earlier, and the second one was to expand and then prune. And let's explore the second one because it's a great complement to the first. Our goal is going to be to take the complex tree that we learned by going too far. Man, you went too far. And somehow chop up some stuff, remove it, and then simplify it in order to come up with what will be a better tree in terms of true error. So here's a kind of a motivational picture. You might end up with a complex tree if you don't stop too early. And you can imagine trying to come up with some fancy way to stop earlier, but instead of doing this, you just go a little too far. And then we're going to backtrack. So we're going to start from this complex tree and we're going to simplify it until I get a reasonable tree that has maybe higher training error, but it has better true error. The fundamental question though is, what makes a tree simpler? Clearly, if you have a super deep tree on the left versus a shallow tree on the right, so in other words, if you're looking at depth, then it is here's a technical term that I like to use, no-brainer. It is a no-brainer that the tree on the right is simpler than the tree on the left. So is depth the measure that we're going to use to qualify what complexity of decision trees is? And it turns out that depth is not a very good metric. And the reason is, the core problem is that some features might have more values than others. And so some features might lead to more splits than others. So here, both trees have the same depth. And so the question is, which one is simpler? And we will see this problem all the time. And intuitively, the more leaves you have, the more complex a tree is. So we're going to introduce this function L of t, which just measures the number of leaves the tree has. And so the tree on the left here has 5 leaves, the tree on the right has 2 leaves, and so we're going to say the tree on the right is simpler. And now we're getting somewhere interesting. So now we can start talking about the complexity of different decision trees. So for example, the super complex one on the left had the number of leaves here was 1, 2, 3, 4, 5, 6, while the one that's too simple on the right, the number of leaves it had was 1. And somehow I want to find a solution in between. And the solution in between will allow us to adapt, that allows you to go deeper in some branches, shallower in others, but try to keep the number of leaves as good as possible. And so just like other areas in machine learning, we're going to introduce some kind of trade-off between these two concepts. The two concepts we're going to trade off, the two quantities, are how well my tree fits the data and what the complexity of the tree is. So the total cost is going to be a measure of fit and a measure of complexity. We saw this in regression, we saw this in logistic regression, we're seeing this again in decision tree. Here, the measure of fit is just classification error in the training data, so training error, and the measure of complexity is going to be the number of leaves, and we're going to balance the two. So more specifically, we're going to use error of t to denote the error, classification error in training data, and L of t to denote the number of leaves. And as we will see, we'll have a magic parameter to trade off between these two quantities. In particular, we're going to use lambda to denote that magic parameter that we can fit then with a validation set or with cross-validation. When lambda equals 0, we're back to the standard decision tree learning process. When lambda is infinite, we have infinite penalty. So we're going to have infinite penalty, which means we're going to just learn a tree that has no decisions in it. So just the root. So we're going to learn something like this, root, and then a class. And in this case, we're just going to say the y hat for all data points is the majority class. In other words, lambda is equal to infinity, we're just going to output the majority class. When lambda is equal to 0, it's crazy deep decision tree. When lambda is in between, that's where we're in game here. So this is going to balance the fit and the complexity of the tree. More specifically, we're going to go from that complex tree to a simpler tree by using a pruning approach where the pruning is based on this function which balances the error of t plus lambda times the number of leaves in t.